Good afternoon students. This video is for class 7 physics and today's topic is conservation of energy. In the last video we had done conversion of energy. In this video we are doing conservation of energy. These are two different things. So let us start. We have read that in transformation of energy, that is conversion of energy from one form to the other, like for example light to heat or heat to light, chemical to light, etc., required form, that is suppose I want to convert light energy, electric energy into light energy. The required form, some part of energy is changed into non-useful or unrequired form also. For example, suppose you are lighting a bulb, you are converting electric energy into light energy, but unwanted heat energy is also produced. Suppose you are in a car, you want to convert chemical energy of the petrol to the mechanical energy of the car, but heat and sound is also created, which is unwanted and unrequired, which is unuseful to us. But the total sum of useful and non-useful energy is same as the energy being transferred. Okay, it means that suppose you are converting 100 joules of heat energy into some amount of light energy, then what happens is out of 100, 80 joule might get converted into light energy, but 20 joules might get converted into any other forms of energy like sound energy, right? Any energy. Another example, for example, if 100 joule of electric energy is converted to mechanical energy, for example, you are using a washing machine, suppose it needs 100 joules of electrical energy, right? In a washing machine, you just want the rotation, that is mechanical energy, right? But the washing machine also produces sound. The machinery parts also get heated up. So what happens is some amount of energy is getting transferred into non-useful form of energy. So in our book's example, 100 joules, it is possible that 60 joules is converted into mechanical energy and the remaining 40 joule may be the hear and the sound energy, that is we might hear it as a sound energy. Thus the law of conservation of energy can be stated as follows: the total energy is always conserved in each transformation of energy. So whenever the energy is getting transferred, 100 joules, if it is getting converted into some other forms of energy, if I add all of them, I should get 100 joules only. I cannot get 101, neither I'll get 99. So which means energy can neither be created nor it can be destroyed. So this is actually law of conservation of energy. Energy is conserved. In mechanical energy, for transformation between the potential energy and kinetic energy, the law of conservation of mechanical energy takes the following form. In the absence of friction, the total sum of potential energy and kinetic energy is always constant, right? When you add at any instant of time, it should give us a constant value in the absence of friction. Okay, the next line, this can be easily understood by the following example. The first one, a roller coaster operates on the principle of conservation of energy. In figure 3.23 here, this one, in figure 3.23, we can see the car going down and here. So what happens is potential energy is getting converted into kinetic energy, right? And here at this point it has maximum kinetic energy and zero potential energy because there is no height. As you all know, for potential energy we need height, and as the car goes up here, again the kinetic energy is getting converted into potential energy. So in all these three cases, case 1, case 2 and case 3, in all these three cases, suppose the car originally had 100 joules, at any instant the total energy, if we add potential energy and kinetic energy, it needs to have 100 joules only at every stage, right? 100 joules, 100 joules and 100 joules at every stage. For example, kinetic energy is 0 here in the first case, right? Potential energy should be 100. So that 100 plus 0 will give me 100, right? If it is 1000, it has to be 1000. If it is 500, it has to be 500. Okay, let us see what does the book say. In a roller coaster, okay, a roller coaster operates on the principle of conservation of energy. In figure, as you have seen the figure, initially some work is done to put the roller coaster car at the position A. This work done is stored in the roller coaster in the form of potential energy since it is stationary at A. Its kinetic energy is 0 because it is not moving. As it starts coming down, the potential energy changes into kinetic energy. So the potential energy decreases and the kinetic energy increases, right? So what happens as it is going down, as this car goes down, potential energy will change into kinetic energy. So at this point, at point B, what happens? The potential energy becomes 0 because there is no height, and the kinetic energy becomes maximum, right? And if this car is going up here, again the kinetic energy is changing into potential energy. As it starts coming down, the potential energy decreases and the kinetic energy increases. So when the roller coaster reaches at B on the ground, the potential energy becomes 0 because there is no height. As I have said, it has converted all into kinetic energy. So the kinetic energy at B is E. That means if it is 100, it will be 100. If it is 400, it will be 400, because all the potential energy has converted into kinetic energy. Due to this kinetic energy, the roller coaster rises to reach the point C. Okay, and again all the kinetic energy will change into potential energy provided there is no friction. Suppose the road is very rough, some energy is taken by the friction also. During the motion from B to C, the kinetic energy changes into potential energy. Therefore, the potential energy increases and again becomes E1, while the kinetic energy decreases from E to E1. Thus, at each position A, B or C, the total sum of potential energy and kinetic energy should remain constant, which is E. Here we have neglected friction, right? Because if we include friction, the calculation will be slightly different. So in figure 3.24 also illustrates the conservation of energy in a roller coaster, showing that at each point the sum of potential energy and kinetic energy is 40,000 joules. So here at this point you can see, let me change the color. Okay, at this point you can see the potential energy is 40,000 joule, and there should not be any kinetic energy, right? Because the stone or the any object is at rest. So once it falls down, all the potential energy will change into kinetic energy, right? The potential energy at this point what happens? Potential energy, suppose the potential energy is 20,000 and kinetic energy is 20,000. when we add them, it should become 40,000. At this point also some of the potential energy again has changed into kinetic energy, but when you add, I should get 40,000. At this point also some of the potential energy has again changed into kinetic energy because the stone is still moving, right? So every time you see, when you add potential energy and kinetic energy, the energy is conserved, it is same, right? So number 2, a ball falling vertically downwards from a height is another example of conservation of mechanical energy. In figure 3.25, when the ball is stationary at point A at the height h above the ground, the potential energy is maximum. Here they are talking about this figure here. The potential energy is maximum here, right? E. And kinetic energy 0 because at position A of the ball, it is at rest. But once the ball is falling down, right? Once the ball is falling down, so what happens is at position B, half of the potential energy will change into kinetic energy because it has moved half a height, right? Now because of this height, it will have potential energy, because of the motion it will have kinetic energy. When you add these two, I should get E. E upon 2, half E plus half E should be 1 E. And when it's about to touch the ground, what happens? The potential energy becomes 0 because there is no height, and all the potential energy has changed into kinetic energy. But at every instant, if you add E plus 0, I'll get E. E plus 0, I should get E, right, in the first case. Second case, E by half E plus half E, again I will get E in the second case. and third case 0 plus E, again I will get E. I hope you understood this, right, during a free fall of a body. As the ball starts falling down, its potential energy changes into kinetic energy. At the point B, at a half of the height above the ground, okay, half potential energy will change into kinetic energy. Like just now I have shown E upon 2 plus E upon 2 should give me E, right? Please try the calculation. On reaching the point C of the ground, whole potential energy will change into kinetic energy, right? And there also E plus 0 will give me E. Thus, we notice that during the vertical fall of a ball, its friction due to air is neglected. The total sum of potential energy and kinetic energy at each point remains same, right? So, activity you can read and try to do it at home. Now, the last topic of the chapter, which is production of hydroelectricity. The water in motion in a river or sea has kinetic energy because it is moving, right? The energy possessed by the flowing water is called hydroenergy. The most important use of hydroenergy is to produce electricity from it, right? We can convert that kinetic energy of water into electrical energy. In figure 3.26 shows the principle of hydroelectric power plant. The flowing water of river is collected in a dam at a high altitude. The water stored in the dam has the potential energy. When the water from the dam falls on the water turbine, the potential energy of the water stored in the dam changes into its kinetic energy, and this kinetic energy of water is transferred to the blades of a turbine as the kinetic energy which rotates the turbine. As the turbine rotates, it rotates the armature of a generator or dynamo, and hence electricity is produced. So now what is dynamo, what is generator, that you have to study in class 10, right? So let me explain here, okay, with the help of a diagram. So what happens here is, you can see this river water is stored in a dam. Which energy will it have? It will have potential energy, right? And when it is flowing down, this potential energy will change into kinetic energy, right? And when this kinetic energy hits the blades of a turbine of the dynamo, right, this blade starts rotating this way, right? This blade starts rotating this way. Actually it rotates very fast. So at this point my kinetic energy will change into mechanical energy, and this mechanical energy moves the this part, okay, this is called coil in the magnet. This is north and south, okay, NNS. So when it rotates in the magnetic field, okay, what is magnetic field we will learn afterwards. When it rotates in the magnetic field, it can produce electricity. So finally potential energy will change into electrical energy. In this case potential energy will change into electrical energy, but in between we have kinetic energy and mechanical energy as well. So this is the end of the chapter energy, right? I have asked you to do the question answers till number 20. Please try to do it and try to sum it as fast as possible. Thank you so much.